Okay, in the last video we were talking about performing operations on complex numbers, and we stopped at the end with the division problem. So we want to rewrite, the idea is we want to rewrite this as a plus ib for some a and some b. Okay, so the way to do that is we'll take 1 plus 2i divided by 3 minus 5i. We want to get rid of the complex number in the denominator, so we multiply top and bottom by the conjugate. Okay, and so let's go ahead and do that. So the idea is the whole idea is that the denominator becomes 9 plus 25, right? And so that's going to be 34. So do you see what we're doing? And now our numerator becomes what? Go ahead and FOIL that out. So it's going to be 3 plus, I don't know if I'm doing this in order or not, 6i plus 5i plus 10i squared. Good. So that's going to be 3 minus 10, which is minus 7, right? Because the I squared is minus 1. And then we have plus 11i. Good. So this is our complex number, right, that represents the division of 1 plus 2i with 3 minus 5i. Good. We're going to learn a different way of dividing that's going to make more sense intuitively in just a second here. But we need to develop the polar form a little bit better. Develop the polar form. Oh geez. Drank too much coffee today. Form for a plus ib. And now we said that that was equal to r cosine theta plus I times r sine theta, right? And just as a quick reminder of our triangle, this is our a and our b, so this point here is a plus ib, which can also be written in terms of b is equal to r cosine theta, right? Or sorry, b is r sine theta, and a is r cosine theta. Good. All right. So now we want to compute take a look at a definition. Consider the definition below. And this is Euler's formula. Euler's formula says that we're going to make e to the I theta. So this is the complex exponential only, right? This is the real exponential function is just the normal real exponential function. So this is just defining the complex exponential function. Is defined to be the complex number cosine theta plus I sine theta. Good. Now I'm saying that this is a definition, but this is actually a theorem, and you can prove this theorem. We're not going to prove this theorem, but it's fun to take a look at the proof. It involves some power series and things, but we're just going to assume that this is true. And so therefore, the polar form of our complex number is r times e to the I theta. Does everybody see that? So I'm just rewriting this, right? And so this is really an interesting expression right here, because, for example, suppose let z be equal to r e to the I theta. What is z squared? What does z squared do to a complex number in the plane? To understand what z squared does to a number in the plane, you can square the complex or the polar form, and you see that that's r squared e to the I 2 theta. And so what's interesting here is that a square in the plane will square the magnitude and double the angle. So there's a rotation involved, right? It's not just going straight out. It's stretching and moving and rotating. So there's a stretch and a rotation involved in a square function. Similarly, if you take the square root of z, right, that's going to be r e to the I theta to the 1/2 power. And so that's going to be the square root of our e to the I theta over 2. And so to take the square root of z then, you would take the square root of the magnitude, but then you would also half the angle, right? So that's kind of fun to look at. And there's another big thing about Euler's formula that's always interesting. I should probably mention it. And that is, if I take e to the I theta equals cosine theta plus I sine theta, and we evaluate everything at pi, what do we get? I sine pi. Okay, well, sine of pi is 0, cosine of pi is -1, and so you get that e to the I pi plus 1 equals 0. And this, if you think about it, is this packs a lot of meaning into it. For example, e is a constant of nature, right? It has to do with growth. I is the square root of -1, and pi is a constant that has to do with a circle, right? 1 and 0 are some of the the symbol of unity and the symbol of nothing. So it's very surprising that you would have a relationship this beautiful. And a lot of mathematics is about the aesthetics of mathematics, and this is such a beautiful expression that it has been voted the most beautiful equation in mathematics for several years in a row. Excuse me, I'm breaking up, going verklempt. Okay, so anyway, you'll see this a lot in The Simpsons as well. That's kind of a fun side note. So as we look at this, I would mention that the rules of exponents apply. For example, if I consider a plus a to the e times e to the power, complex power, a plus ib, you would rewrite that as e to the a, which is the real exponential, times e to the ib, right? And so this would be your cosine of b plus I sine of b, right? And so this is a real number times a complex number, and so you could compute that as usual, right? Good. Similarly, I think I've already mentioned that if I take e to the I theta times e to the I beta, right, that's going to be e to the I theta plus beta. So you would add the angles together. And I think finally I might note that if you think about this as an ordered pair, if you think of e to the I theta, which is cosine of theta plus I sine theta, right, and you associate that with the ordered pair that in the plane, cosine theta sine theta, what you realize is that e to the I theta is a point on the unit circle. So e to the I theta is a point on the unit circle in the complex plane. So it's real and imaginary. Okay, so sometimes that's kind of handy to remember. E to the I theta does not blow up. E to the I theta just goes around the unit circle. So in particular, right, if we were to increase theta, for example, as theta increases, e to the I theta is periodic. It does not blow up. Okay, so that's going to be useful when we talk about some examples in the complex plane. Good. All right. Well, I've got a little bit of time here, so maybe I'll just talk briefly about the logarithm since we're talking about the exponent. It's good to think about the logarithm while we're in it. Good. So suppose I want to take the log, we're going to take the natural log of a plus ib. Well, if we were to just follow our nose kind of in how we might do this, just like before, we might convert a plus ib into its polar form, r e to the I theta, and then assuming that the usual rules of logarithms apply, this would be the natural log of r plus natural log of e to the I theta. And again, assuming that the usual rules of logarithms apply, we can simplify that. And in fact, this does work. And in fact, you see that the natural log of a complex number is the natural log of its, the real part of it is going to be the natural log of its magnitude plus I theta, where theta is its argument. Good. So, yeah, what's interesting here is that we can now take, what's the natural log of minus 3? Well, remember that in the complex plane, minus 3 is equal to 3 e to the I times pi, right? And so the natural log of 3 is equal to the natural log of 3 e to the I pi, which is the natural log of 3 plus I pi. Good. So we can now take the natural log of negative numbers. That's fun. The one thing I should say is that the what is the polar form of z equals 0? Well, the argument of 0 is not defined, right? So we should say the argument of 0 is not defined. It's left undefined. Okay? So you might say, well, the r is equal to 0, so the theta could be anything. But that's kind of why the argument is not defined for 0. So you still can't take the logarithm of 0 because the real version of that's not defined, right? But you can now take the logarithm of a negative number. Okay, I've gone over time. We might briefly talk about complex numbers in the polynomials. Okay, so the next video will just be a few exercises.